For as long as we have been studying the science and history of our universe, the Big Bang has been the explanation for everything. There have been hundreds of studies and thousands of scientists who have worked on the research, and according to the data, the Big Bang has been the leading theory explaining how the universe formed. Dark energy was believed to be the largest energy source, even larger than galaxies. Dark energy is the anti-gravitational force that creates the expansion of the universe. But science today is very different from what it was before, and with technological improvements come new theories. We often realize that things we believe to be 100% true are far from being true. Well, that just happened again. The images captured by the James Webb telescope of new galaxies are impressive, but for scientists, they are surprising and challenging. These galaxies are smaller, softer, older and more numerous than expected, causing panic among them. These images directly contradict the Big Bang hypothesis, which has been considered an unquestionable truth. The galaxies observed are much smaller than expected for an expanding universe, and their softness and age also defy expectations. Furthermore, the number of galaxies observed is much larger than predicted, raising questions about the accuracy of the Big Bang hypothesis. According to the Big Bang theory, at the beginning of the universe, all the matter, energy and fundamental blocks of the cosmos were compressed into an extremely small and dense point, called a singularity. The infinite density within the singularity implied an enormous amount of mass and energy concentrated in a tiny space. The universe subsequently underwent expansion and inflation for approximately 13.7 billion years, leading to the formation of galaxies, stars, and other cosmic structures. Cosmic inflation played a key role in smoothing out irregularities, homogenizing the distribution of matter and energy, and setting the stage for the evolution of the universe as we know it today. As the universe expanded, its expansion rate slowed, but it still continued to expand measurably, known as cosmic expansion. This expansion has been observed through the redshift of light from distant galaxies. During this process, since the Big Bang, the universe underwent transformations and nucleosynthesis, the creation of light elements such as hydrogen and helium. These elements laid the foundation for the formation of stars, galaxies, and more complex cosmic structures. The existence of cosmic background radiation, CMB, is significant evidence of the Big Bang theory, as it aligns with its predictions and supports the idea that the universe was in a hot, dense state before its expansion. Taken together, this evidence provides strong support for the Big Bang theory. Cosmic background radiation, CMB, offers us a window into the beginnings of the universe, confirming the Big Bang theory as the most accurate explanation of its origins. Several lines of evidence support this theory, such as the redshift in distant galaxies, which shows the continued expansion of the universe. Furthermore, the abundance of light elements and the distribution of large-scale galaxies also agree with Big Bang predictions. The gravitational force has been essential in shaping the distribution of matter and the formation of galaxies, and the filamentary and network structure we observe aligns with the gravitational effects predicted by theory. Together, this evidence supports the idea that the universe began in a hot, dense state and has evolved through expansion over billions of years. Images from the James Webb Space Telescope challenge what Big Bang theorists thought about the growth of galaxies. Small galaxies were expected to evolve into larger galaxies through collisions and mergers, but observations show smooth, well-organized galaxies, calling into question the frequency of these processes. This suggests that galaxies were never small to begin with. Furthermore, the optical illusion predicted by the expansion of the universe, where objects appear smaller with distance, has not been found. As for stars, their color can help determine their age since their lifetime is related to the amount of fuel they burn. The James Webb Space Telescope has observed distant galaxies that appear to be older than expected according to the Big Bang theory. Some of these galaxies show stellar populations more than 1 billion years old, which contradicts the idea that nothing should have existed before the Big Bang itself. Additionally, James Webb images have revealed a large number of massive galaxies, challenging the premise that the number of galaxies would decrease with distance in the past. These findings call into question the plausibility of the Big Bang theory. It is interesting to note that the Big Bang theory presents 16 incorrect predictions in the scientific literature, which is significant. For example, the estimate of the abundance of helium and lithium is higher than expected, and there are unexplained phenomena, such as the absence of the expected illusion of the size of objects as the distance increases. Despite these contradictions, criticism of the theory has not been widely disseminated in the media, possibly due to resistance from certain groups and dependence on funding for cosmology research from sources controlled by supporters of the Big Bang theory. This situation can make it difficult to obtain funding for alternative research and hinder scientific progress in exploring other theories. Years ago, if researchers could fund their own cosmology research as a side pursuit, they still had the opportunity to publish heretical papers. However, the system also blocked them. These documents were often ignored by the established cosmological community. As the crisis within the field of cosmology became evident in 2019, the cosmological establishment rallied to protect the failed Big Bang theory through censorship, as it lacks alternative defenses. It has now become extremely difficult to publish papers that are critical of the Big Bang theory in astronomical journals. Even if someone wrote a document, it would likely never see the light of day. This brings us to a crossroads point. If the Big Bang theory is not really accurate, how could the universe have formed? Surprisingly, there are some theories that could explain it all. The steady-state theory is one of the most popular, and proposes an alternative explanation for the nature and origin of the universe. According to this theory, the universe is in a perpetual and unchanging state, meaning that it has always existed and will continue to exist indefinitely. Unlike the Big Bang theory, which suggests a point at which the universe began, the steady-state theory suggests that it has always been there. One of the key aspects of this theory is the concept of continuous creation, which proposes that matter is constantly being created throughout the universe to compensate for the apparent expansion of space. In other words, as galaxies and other celestial objects move away from each other, new matter is continually generated to fill the empty spaces and maintain a consistent matter density in the universe. This idea of continuous creation serves as a way to explain the observed expansion of the universe without the need for a singular event like the Big Bang. Another theory is eternal inflationism, which introduces the idea that our universe is just one component within a much larger multiverse. According to this theory, the multiverse consists of numerous bubbles of universes, each with its own unique set of physical laws and properties. These universal bubbles exist alongside one another, occupying separate regions within the broader multiverse. The key feature of the theory of eternal inflationism is inflation, which refers to the rapid expansion of the universe that is believed to have occurred shortly after the Big Bang. In this theory, inflation is not a single event limited to the initial stages of our universe's existence, but rather an ongoing process that continues to take place in specific regions of the multiverse. During periods of inflation, certain regions within the multiverse experience rapid, exponential expansion, leading to the creation of new universal bubbles within those regions. Each newly formed universe within the multiverse possesses its own distinct physical laws, constants, and properties, resulting in a vast collection of diverse universes. There is also the cyclical universe model, which proposes a pattern in which the universe goes through a series of repetitive cycles. Each cycle begins with a Big Bang, a tremendous explosion that marks the birth of a new universe, and concludes with a big crunch, a dramatic collapse where the universe contracts back into a highly dense and hot state. In this model, the universe goes through an expansion phase after the initial Big Bang. During this expansion, galaxies, stars, and other cosmic structures form, and the universe gradually becomes larger and less dense. But the expansion eventually slows and reverses due to the force of gravity exerted by matter and energy in the universe. As the expansion slows, the universe enters a phase of contraction known as the Big Crunch. During this phase, the universe becomes increasingly compressed and denser, leading to a highly compact state. Ultimately, all matter and energy in the universe is concentrated in a singularity, a point of infinite density and temperature. After the Big Crunch, a new cycle begins with another Big Bang, and the process repeats itself, leading to an eternal cycle of expansion, contraction, and rebirth. These theories offer interesting explanations for the existence of multiple universes and the remarkable diversity observed in our own universe. Could this be the definitive proof we need to debunk the Big Bang theory? But in a recent effort, researchers turned the Webb telescope toward the remarkable Whirlpool Galaxy M51 and discovered intricate details of the empty cavities and bright filaments in the galaxy's expanding spiral arms. Although it might not seem like a phenomenal discovery, this is the image scientists have been waiting for. This hypnotic image, just released, allows us to look inside a spiral galaxy that is located about 27 million light-years from our planet. The dark red regions trace the warm filamentary dust that permeates the middle of the galaxy. Red regions show reprocessed light from complex molecules forming in dust grains, while orange and yellow colors reveal regions of gas ionized by newly formed star clusters. Using two of its most powerful instruments, the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, the James Webb Telescope has given us two perspectives of the celestial object. Both devices are designed to capture the distant universe, decoding infrared light signals emanating from distant stars and galaxies. Located 27 million light-years from Earth, the James Webb Telescope image is one of a series of observations aimed at shedding light on the interplay between stellar feedback and star formation in environments outside our own galaxy. The Milky Way, first discovered in 1773 by French astronomer Charles Messier, the Whirlpool Galaxy, also known as M51, is one of the best-known objects in the night sky and is part of the Messier catalog. M51 is named Whirlpool because of its rotating structure, similar to water around a drain. It is located 27 million light-years away in the constellation of Canes Venatici, so the image we are seeing is of the Whirlpool Galaxy as it was 27 million years ago. But never before have we seen an image like the one captured by the James Webb Space Telescope, the most powerful of its kind. This new image not only represents a journey through space, but also a journey back in time. The stellar feedback has a dramatic effect on the middle of the galaxy and creates a complex network of glowing knots and cavernous bubbles, according to the European Space Agency, which helped build the telescope and launched it into space last year from its spaceport in the French Guiana. Stellar feedback is the term used to describe the energy output of stars and the environments that generate them, and is an important mechanism for influencing rates of star formation. According to the agency, understanding stellar feedback is critical to developing accurate universal models of star formation. The Whirlpool has a little brother, whose gravitational effect is assumed to be partially responsible for the galaxy's distinctive well-developed spiral arms. When Hubble captured an image of M51 more than a decade ago, the team behind it said they couldn't wait to see the same image with the planned James Webb Telescope. This observation of M51 is part of a series titled Feedback in Emerging Extragalactic Star Clusters, called FEAST. And that's what James has achieved with his discovery of the Ring Nebula with his advanced suite of infrared sensors. The James Webb managed to obtain images that provide unprecedented spatial resolution and spectral sensitivity in all that cosmic chaos, according to the ESA statement. What this means is that the Space Telescope, which is located about 1 million miles, 1.6 million kilometers, from Earth, was able to reveal details about the intricate structure of the Ring Nebula that scientists simply hadn't seen before. When we first saw the images, we were amazed by the amount of detail in them. The bright ring that gives the nebula its name is composed of about 20,000 individual clumps of dense molecular hydrogen gas, each as massive as Earth. Within the ring, there is a narrow emission band of polycyclic aromatic hydrocarbons or PHs, complex carbon-rich molecules that we would not expect to form in the ring nebula. Outside the bright ring, we see curious peaks that point directly away from the central star and are prominent in the infrared, but barely visible in Hubble Space Telescope images. We think this could be due to molecules that can form in the shadows of the densest parts of the ring, where they are protected from intense direct radiation from the hot central star, for example, by capturing wavelengths of infrared light emitted by the nebula. Also known as wavelengths of light invisible to the human eye. The James Webb revealed information about the filament structure of the inner rings, as well as approximately 10 concentric arcs in the outer regions of the phenomenon. These target-shaped features really surprised. These rings must have formed approximately every 280 years as the central star shed its outer layers. When a single star evolves into a planetary nebula, there is no process we know of that has that kind of time frame. Instead, these rings suggest that there must be a companion star in the system, orbiting at a similar distance as Pluto does from our Sun. As the dying star shed its atmosphere, the companion star shaped the flow and sculpted it, offering this explanation. It's also important to note that this isn't the first time James Webb has trained his hexagonal golden eyes on the ring nebula. Very recently, the machine captured this portion of the universe in high resolution, and scientists added green and purple filters to create a glorious scene for us to admire. The history of observing the ring nebula means more than its physical components. It is a symbol of human curiosity and advancement. From the early misconceptions that led to its label as a planetary nebula to the advanced technology of James Webb, our quest to understand this phenomenon reflects the growth of astronomical science itself. The ring nebula was discovered in 1779 by astronomers Antoine Darquier de Pellepux, Charles Messier, and was added to the Messier catalogue. They found it while trying to follow the path of a comet through the Lyra constellation. Today, the ring nebula stands as a symbol of astronomical archaeology. The colorful main ring, the remains of a dying star on its way to becoming a white dwarf, is a vivid reminder of our cosmic connection. When studying the nebula, we are not just observing a distant object, but we are looking at the past, present, and future of the universe itself. Our own sun may have a nebula when it finally expires in about 5 billion years, and will become a white dwarf, although we almost certainly won't be here to see it. It may seem strange that two different images of the same nebula would have such different colors, but the Webb observes objects at infrared wavelengths, which means our eyes literally can't handle the Webb's raw images. Webb's image data simply appears black before Webb's image processors translate the infrared data into visible wavelengths of light, which they did with the image to highlight certain aspects of the nebula in each image. From some of the deepest views of the universe to studying the rings of planets in our own solar system, the Webb is offering astronomers a whole new view of space. What discovery do you expect next from Webb?